Hello, everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Omega, a nonprofit focused on facilitating AI safety progress. The purpose of these events is to accelerate the Guaranteed Safe AI research program. It's a research program to build AI systems with safety guarantees using explicit world models, formal safety specifications, and verifiers that yield proofs or probabilistic bounds about behavior. So today we have the pleasure of hosting Clark Barrett, director of the Stanford Center for Automated Reasoning and co-director of the Center for AI Safety, with a talk entitled When AI Meet AR. The session is 1 hour, usually, you know, 30, 40 minutes presentation followed by discussion. We can have questions during the talk, just raise your hand. So thank you so much for being here, Clark. The floor is yours.
All right, great. Um, so let's get started here. So AR, when I say AR, I mean automated reasoning. And there's this interesting interplay between AR and AI. So on the one hand, we have automated reasoning, which, 20 years ago was just theoretical curiosity, but now it's become a mature technology. There are many applications, informal verification, theorem proving. It's used extensively in industry, places like Amazon, Apple, other hardware vendors. And the great thing about these techniques is they provide correctness guarantees. But of course, scalability is one of their main bottlenecks. So on the other hand, we have all these new AI techniques, which are very powerful. They're very good with messy, ill-formed problems, which is great, data-driven, but unfortunately, no correctness guarantees. ML systems have adversarial inputs. Gen AI produces hallucinations. So these are in some ways complementary. And so what I'd like to talk about today is, can each of these two areas help each other in various ways? So first, I'm going to look at how AI can help AR with scalability, and then I'm going to look at how AR can help AI with correctness. So for this first project, I'm going to talk about something called lightweight online learning for sets of related problems. This is joint work with a bunch of people, mainly led by my student, Andrew. So here's the idea. We have these automated reasoning tools, SAT solvers, SMT solvers, so on, used a lot tackling hard problems. Scalability is their big concern. And then we have machine learning that can be used for various things. And people have tried using machine learning to tune solvers. And basically, well, there's various ways that people have tried to use it. One is you just replace the solver, right? Just say, instead of running a solver, I'm going to use this machine learning thing. That doesn't work very well. It's, first of all, you don't get you lose the correctness guarantee, which is kind of the whole point. And then it actually doesn't scale usually as well as custom solvers. On the other hand, what's maybe a bit more promising is to replace some heuristics with some trained ML models. And this can be helpful, but it does have quite a large overhead. Um, you know, there's this really famous work presented at the SAT conference in 2019, called Crystal Ball, and they basically did a whole bunch of work to find out exactly which features should be used to determine the branching heuristics based on a bunch of ML training. And what they found was it was pretty much exactly the features that are already used in the custom heuristics inside the SAT solver. So that was a bit of a disappointment. But still, you can get some mileage here. And then meta-algorithmic design is basically tuning the parameters for that are used for your solver. And this has been quite successful. By auto-tuning parameters, you can essentially beat the best solvers at the SAT competition. However, training offline has some problems. So basically, what you have to do is you have to guess what the problem distribution will be that you're interested in, collect a bunch of training data, and then do the training. Um, Now, on the other hand, what if you get a new problem? Uh, you might like to do online training. So you would get the new problem, compute the features for it, and select the algorithm all online. Why might you want to do that? Well, first of all, if you do offline training, you might get the wrong distribution, right? That distribution may not match the new problem that you have. It's also not really fair. It's not really automated to do this, right? You're sort of putting in a whole bunch of work ahead of time in order to get some speed up when you run the tool. And again, it only works for a particular distribution. So something that's a bit more fair and truly automated is this online approach. And that's what I'm going to talk about today. So I'm talking about self-driven strategy learning. And the idea is suppose you have to solve a set of related problems, but these are new and you don't have any prior knowledge about their distribution or features. Can we somehow um, use the fact that you're solving a set of problems to do some training and learning so that by the time we solve all the problems, we get a speed up? And there are some quite interesting problems that do fall into this category. We'll focus on the first one here, bounded model checking. Bounded model checking has the additional advantage that you typically start with a small unroll and increase it as you go. And so you can learn something from the smaller unrolls that you could use at larger unrolls, and we'll see how that works. Okay, so the key idea is we're going to collect and learn on the fly as we solve the problems in S. Okay, so here's a sketch. Suppose we have a set of related problems, I1, I2, etc., and we have some search space of strategies for solving those problems, which we'll denote with these V's. Then what you normally would do is, okay, let's just check the first problem, we'll pick a strategy, say V0, and we'll just check all the problems with that strategy, right? So what we're going to do instead is we'll solve the same problem multiple times with different strategies, and we will determine the cost of solving that problem with that strategy. And then after a while, after we collect some data, we'll do some training to try to figure out which strategy works best for which problems, and then we'll use that training to decide which strategies to use going forward. Okay. So what about this overhead of training, right? Well, the idea is that we're going to hopefully amortize that the data collection overhead by getting some big wins on the harder problems. We can also view this as a logical calculus. So we have this sort of next rule that says we're checking using some strategy. If we fail, we're done, right? So in this case, we're looking for uh, sorry. Success is if you get a SAT answer. So basically, we assume a set of related problems where if you get SAT, you're done. But otherwise, we're just trying to determine unsat for all of them. And then we have these different phases: collecting, training, and choosing strategies. So if you're interested, you can read the paper for the details, but this gives us a nice sort of abstract way to talk about what we're doing. So basically what we do is next means go to the next problem. So every time we go to the next problem, we collect some data on that problem, and then we reapply the training tactic. Um, every time we go to a new problem, we also apply strategize to pick the new strategy. And basically, once we exhaust some learning budget, we stop collecting data and we just strategize for each new problem. Okay. So we're going to do a case study with bounded model checking, right? So as you probably know, bounded model checking is widely used technique for hardware. It's useful for finding bugs. It doesn't by itself establish formal guarantees other than saying like within some window, some bound, we have a guarantee. So we're going to check for the property over some execution bounded by K. And you can write this as a satisfiability problem where you take the initial state, you take K copies of the transition relation, you take K copies of the property, and then you try to check whether the property does not hold at the next state, right? So this is a standard BMC query. And typically you, like I said, you start with K equals 1, and then you gradually increase K to solve harder and harder problems. And here we have S is a step size. So maybe you don't jump from 1 to 2, maybe you jump from 1 to 5 or 1 to 10. This sometimes helps, as we'll see. Okay. So for our case study, we used benchmarks that were not solved in the hardware model checking competitions a couple of years ago. And we used the SAT solver KISSSAT, either running the default configuration or with our self-driven strategy learning. And the strategy space was defined by looking at some experts who identified essentially 2 to the, what is that, 15 or something. Anyway, a strategy space of some size, around 8,000 different strategies. Okay. And we use some sampling techniques to do the data collection. Okay, so let's look at some results. So here's the basic idea. So what we see is that if you run standard bounded model checking, as the bound increases, you get an exponential increase in the solving time. And if you use our technique, you get a moderate increase for low unrolls, but then you flatten that exponential curve as you get to harder and harder problems. And in fact, once you get to, say, a bound of 35, you're looking at a 2x reduction in runtime, which is pretty good. And this is pretty typical. So in 90% of the cases, we were able to certify larger bounds. And even compared with state-of-the-art model checkers, it improves. I think it's not important to go into these details. They're also maybe a little out of date. But basically, we're able to solve, some problems that aren't solved by the virtual best of the other solvers in the hardware model checking competition a few years ago. All right. So that's one side of the story. That's a way that we can use machine learning to help automated reasoning tools. Let's look at the other side. So how can we use, and this may be a little more interesting to this community, so I wanted to get to this quickly. How can we use formal tools to provide correctness guarantees for AI-generated content? So I'll first tell you about this work called Clover. And basically the idea is if you're using Gen AI to generate code, you can also use it to do formal. So let's see what I mean by that. So we all know that language models are very good at code, getting better all the time. They can synthesize simple, even not so simple programs. But there's a big issue, right? How do we know the code is correct? And how do we protect ourselves against a future where we have, millions of lines of AI generated code with who knows how many bugs in it, right? Um, so what we can do is, how about instead of using the language model to generate just the code, we also have it generate the formal specification, and then we use a formal tool to check whether that specification is actually correct. All right, so basically in this paper, we identify 2 phases. So the first phase is somehow you you generate some stuff, and then in phase 2, we're going to check that what's generated is actually okay. And we're going to do this in a somewhat sophisticated manner. So we're going to require the generation phase to produce 3 artifacts, not just the code, but also some formal annotations and some natural language doc strings. And then in the verification phase, we're going to check consistency among all 3 of these artifacts with 6 one-way checks. And we're going to do this all based on a paradigm of deductive program verification. So just to remind you, in case you're not familiar with this, the idea in deductive program verification is you write pre and post conditions for every function in your program, and you write loop invariants for every loop. And then you generate verification conditions that try to prove uh, that basically each loop-free path connecting uh, a pre-post condition or an invariant uh, preserves, basically under the assumption that the first thing holds ensures that the second thing holds. And this is, using standard techniques pioneered by Floyd and Hoare and others. But not really used that much in practice because it's a tremendous amount of work to write all these pre and post conditions and invariants. Okay, but if you do have your pre and post conditions and invariants, you can check automatically using formal tools whether your program is correct with respect to those specifications. Okay, so in the first set of experiments I want to talk about is it realistic to assume that we could generate code and annotations? So this is already a few years ago, so things are much better probably by now. But the idea is for we had a set of maybe 50, 60 simple single function tasks. And for those tasks, the code generation was correct already most of the time. And the formal specification generation with some feedback is also correct, in a majority of the time. So, and I'll come back to this. I'll talk about another project at the end of this talk where we did a deeper dive into this annotation generation and showed we can even do a lot better than this. So I think it's realistic to say that we can generate code and annotations. So then the question is, how do we know if they're correct? So this is where we get into this verification phase. And so the idea is, well, the most obvious thing we can do is we'll check whether the code satisfies its formal annotation. And this is done with a formal tool. Here we used the Daphne and Varus tools. Daphne is its own little language for doing deductive verification, and Varus is a tool for doing Rust verification. Okay, now this is great, but there is one little issue, which is what if, I generate the annotation that just says true everywhere, right? So my code will absolutely pass that formal spec. Every piece of code satisfies the true specification. And so just this check by itself is not sufficient. So the next check we do is sort of to mitigate that issue. And what we do here is we look at the formal spec by itself. We ask a separate instance of an LLM to generate code that matches that specification. And then we do an equivalence check between the original code and the generated code to see if they match. Okay, so now if your formal spec is something trivial, there's no way that you'll get the same code back. So that helps solve that. And then we do some checks with the docstring. So we check whether if you asked for natural language from the formal spec, what do you get? If you ask for the formal spec just from the natural language. And after each of these generation phases, we do these equivalence checks. And I'll tell you a little bit more about how we do that. Or maybe I won't. Let's see. Yeah, I'll just briefly mention it. So to check that two pieces of code do the same thing, we have a set of unit tests for the code. You could also do something more sophisticated like formal equivalence checking that we left to future work. To check that two formal specs are equivalent, we can actually, again, use the verifier. We just say, are these two logical specifications logically equivalent? We can check that. And then to check that two docstrings are equal, this is sort of the most fuzzy part. We just, again, ask another LLM to tell us whether these two docstrings are essentially saying the same thing. Okay,
There's
so what?
a quick question in the
Yeah.
chat. Um,
Okay.
Step two may generate different code. How do you compare the code to be equal?
Yeah, so we run unit tests and compare the outputs. So we're looking for functional equivalence of the code. We're not looking necessarily in this project, we weren't looking at whether they have the same, time complexity or anything like that. We're just looking at functional equivalence. And, to be fair, we're also looking at problems that are simple enough that you can write a deterministic formal specification. Again, future work would be how do you handle, non-determinism, things like this. Okay, so the kind of exciting outcome here is we had 60 programs and we had our own, we verified these 60 programs so we knew they were correct by hand. Um, and then we modified each of the 60 programs in some way, in three different kinds of ways to either mess up the specification, mess up the natural language, or mess up the code. And what we found is that we were able, with one shot, we were able to correctly identify 75% of the programs as correct, that were correct. If we did 10 iterations, that went up to 87%. But sort of more importantly is we rejected every single wrong example. So no matter how we modified the code to make it wrong, these checks were very thorough and were able to identify the problem. Okay, so just some limitations of this. We were using GPT-4. We've tried some similar stuff with more modern models, and there's still some limitations, of course. Sometimes we run into trouble with the formal tools. They can't prove the thing that you're trying to prove. And yeah, there's like I mentioned, we're only handling functional properties. And there's still this sort of question that what if all three of these are consistent, but it's still not what the human wanted? So there is this sort of additional requirement that you should have a human in the loop to at least read the natural language and make sure that they agree with what the computer has done. Okay, but these results are quite promising, and I think, I'm sort of all in on the bet that bringing AI and AR together will give us a roadmap to safe, secure, and automatically generated code in the future. Okay, so now I'm going to switch gears a little bit again. And basically, this was a talk I was giving about a year ago. I'm going to tell you what I did in the year since because I got excited about this work. So I really think that AI is a fantastic catalyst for the field of formal methods. So why is that? Well, people are concerned, right? So they're concerned about a future in which AI systems create mountains of buggy software. They're also concerned about a future in which AI systems dramatically increase the capabilities of black hat hackers, right? So on the one hand, AI might generate bad code. On the other hand, it's easier to identify vulnerabilities, right? So we're sort of getting pinched from both sides by AI. And of course, in the AI safety community, maybe formal is going to be the key to ensuring safe AI. So with all of these catalysts, what's happening? Well, there's a lot of excitement around AI-assisted theorem proving, lean. As many of you probably know, there's a bunch of startups in this space. I've talked to most of them, and what I noticed, and this is maybe a little bit unfair, but I'm gonna take some license here. So what I noticed is their pitch seems to be like this. Hey, I can get a gold medal in the International Math Olympiad today, which means tomorrow I can verify all software. So please give me a check for $100 million. And this works, right? So people are excited. People think that, we can get from here to there. So what do I think? Well, I am actually very hopeful and excited about this possible future, but there is a lot of work to do to make this dream a reality. Okay, so it's not as simple as if I can prove theorems in Lean, I can verify software. So let me tell you about what needs to be done and what I'm trying to do to make that happen. Okay, so I'm going to tell you about the CSLib initiative. So the CSLib initiative is brand new. We launched it just last summer. These are some of the people involved in the leadership. And so it's great. We've got, backing from DeepMind and Amazon and interest from lots and lots of people in academia and industry. And what is the idea? So the idea is to build an open source Lean 4 library built through a community effort, formalizing all of computer science. A very modest, ambition. But the idea would be that we have at least three different potential uses for this. So one is it can be used for education. Great. So if you're teaching computer science, you can use these Lean libraries, help people understand things formally. Great. The other is, though, if you want to actually do real hardcore formal methods with real code, we would like to build up an infrastructure in Lean that lets you do this. And this is sort of where I said there's this big gap between can you prove theorems in Lean and can you verify real software. I'm going to go into everything that's sort of in that gap. And then I think it's also exciting for AI researchers if they want to build AI tools that can reason about code. This will provide a lot of data for that and a lot of sort of benchmarks. Okay, so we're going to build this all on top of Lean. Why Lean? Well, we're inspired by MathLib, right? So MathLib is this community effort to formalize all of mathematics in Lean, and it's had tremendous success. It's been really influential. It's changing the way that mathematics is done, and we'd like to do something similar for computer science. So what goes into this CSLib ecosystem? Okay, so and in particular here, I'm going to talk. Um, I'm sort of focusing on the thing that I'm most interested in, which is how can we use the CSLib ecosystem to verify real code? So we're developing a new language, verification-friendly intermediate language called Bool. This will be embedded as a DSL in Lean, and it's defined using a new framework that was recently open sourced by Amazon called Strata. Strata gives you a set of tools for defining domain-specific languages, for extending them, and for building backends for them. It's pretty cool, and we've been working closely with the Strata team, developing some new stuff for them and seeing what they're doing as well. Uh, okay, and then CSLib, the idea is we're going to have a library that basically has formalizations of lots of general CS knowledge. So algorithms and data structures written in Bool, specs and proofs in Lean, and lots of computer science specific stuff. Okay, and then, the real kicker is can we use this now to build tools for real programming languages like Rust, Python, and C?
We have a question.
Yes, go ahead.
Just wondering how far you're planning to take the kind of CS knowledge piece. So the things that seem like they would be incredibly valuable to be able to prove are kind of at the boundary of CS and like things like hardware. So like could you formalize a proof that code does not implement a rowhammer attack? Is like a really valuable thing, but kind of is at the border of what you would normally call CS.
Yeah. Um, I think, our ambition is unlimited. So we'd like to build a platform and like just see what we can do with it, right? And, anything that you can formalize in Lean is on the table. So, I don't know how to formalize that thing, but maybe you do, or maybe someone figures it out. Great. We'll probably start simpler than that. Obviously, we have to start simpler, but I have faith that if we start simple and get a lot of people excited, we'll start being able to do some really exciting things.
There is another question asking
Yeah,
about a little bit more details on the Bool language.
yeah, I can tell you a little bit more in just a second. Um, so why don't we come back to that? Okay, so here's the sort of one way to visualize it here. You're writing some code, or maybe AI is writing some code. in some high-level language. You also have your specifications in that high-level language. Then you would have a translation that generates bool code and lean verification conditions. These would go then to you could either prove these by hand in lean or again use some AI assisted or AR assisted theorem proving, and then you get your proof. Let me show it in a little more of a system architecture vision, which looks like this, right? So you would start with some high level language. Um, there's a lot of this that's not done yet, right? This is the vision. I think this first step of doing a verified transpilation from a front-end language to bool is very hard. So probably first we'll do an unverified transpilation, but that's the ambition. If everything's done in lean, you could eventually say, here are my semantics of Rust, and with respect to that, I've proven that I've generated the correct bool, right? That would be great. I hope somebody does that. Okay, and then once you have the bool code, we have a couple ways to generate verification conditions. We've been talking with the team, Ilya Sergey's team at Singapore. They built a tool called Loom, and it has a shallow embedding of a boogie-like or a bool-like language in Lean, and we can actually translate from bool to that language and use that as a backend. But our main effort has actually been on this deep embedding in Strata because we think it's going to give us more flexibility and more power in the long run. But anyway, it doesn't matter. We can have multiple backends. The important thing is if you can prove this theorem that says the code is correct, right? And any way you prove that theorem is okay with us. The thing that's cool about this though is that all of these either of these backends end up with a verification condition as a lean conjecture. And now we can take all of those excited people who are proving Math Olympiad problems and say, great, can you use whatever you did there and prove our verification conditions? Um, and in fact, there's a lot of efforts out there. So that within Lean itself, there's the grind tactic, which is becoming more and more powerful. We've built a tool called Lean SMT. I'll tell you a little bit about. There's an ongoing effort to build a full-blown Lean hammer, which will leverage multiple tools. And then, of course, there are LLM-based provers and other AI-based provers that are all very promising. So we do want to leverage all of the excitement around proving theorems in Lean, but we think we need all of this other infrastructure if you really want to use that for software or hardware. Okay.
There is a question here also.
Yep, go ahead.
In the chat, what is meant by shallow embedding, deep embedding here?
Okay. Yeah, I threw those around. Those are a little jargony. So shallow embedding means that your DSL is just syntactic sugar around the Lean programming language itself. Okay, so basically you've created a DSL that just can get sort of rewritten into Lean code. Deep embedding means that you define an abstract syntax data structure in Lean, and your code compiles down to that. And then you can prove theorems about instances of that abstract syntax tree. So the deep embedding gives you a lot more flexibility, right? You can sort of define anything you can imagine. The shallow embedding, as long as your DSL is representable as Lean code, the shallow embedding works. So what's interesting is the team that's built Velvet and Loom has sort of exceeded all expectations in what they can do with a shallow embedding. It's pretty impressive. They have, crazy new monads that do this and that, and they have ways to do cool things. So that's great, and I'm excited to see how far they can take it. But we're not putting all our eggs in that basket because we think that there will be some constructs that do not compile down to Lean easily. Maybe you want to reason about concurrency or low-level pointer arithmetic or something, right? So, but everything's on the table. We're excited by all the different approaches that people are trying. Okay. I'll say just a little bit about Lean SMT. So this is a big project involving a lot of people to build essentially a way to prove theorems using SMT solvers, theorems in Lean. So the idea is we're going to use our CVC5 prover, which can produce proof certificates that can then be replayed in the lean prover. So the idea is you start with some goal in lean, you do some pre-processing in lean to get some equivalent goal that's easier for the SMT solver to solve. Then you translate it into an SMT query. You run the solver, you get a proof, and you reconstruct the proof to solve the original goal. I think I'm going to skip this stuff and give you a demo. Let's see. Okay, can you see this?
Yes.
All right. So on the left here, I have some different lean conjectures. And it's not so important what these are. This one here is something about some uninterpreted functions, make some assumptions about predicates P1, P2, and P3. And then
If you can zoom in one notch or two, that
sure.
would be helpful.
Is that better?
Yes.
Great. Okay. All right. So if you look at this little problem in lean, and you come over here, what you see is here it gets translated into this SMT query. Okay, so this is the SMT query that's equivalent to that conjecture. Actually, let's start here. Here's the, let's see. Where do I get? Here we go. So here's the actual lean problem that we're trying to prove. Here it is translated into SMT, right? And then we call the solver, we get back this proof. So this is a proof in the what's called the CPC proof format, which is a custom format that CVC5 defines. But now what we can do is we can take this proof and we can reconstruct it into a lean proof right here. And at the end of the day, let's see, we have goals accomplished, right? So it proved this automatically. We can also do something kind of cool here. So here's a theorem that's not true. And what we get back is we actually get an assignment to X, Y, and Z that makes it not true, right? So the SMT solver is able to tell us, hey, I don't think your theorem is true, and here's why. Here's an example where it fails. So that's useful. This is just with this plus model feature. And then you can prove, some other things too. So we have this integration with this other tool called Lean Auto that can do monomorphization and basically translate some of the more difficult dependent type theory stuff down into first order logic so that we can still solve it with Lean SMT. All right, so Lean SMT there was a paper about it in CAV. It's available, it's open source, you can play with it. A number of people are building things on top of it, and we're going to use it in CSLib. Okay. Let me tell you, yeah.
There was a question a bit before the demo,
Okay.
but also thanks for bringing a demo. I think that's cool. But I'm just gonna read the question. Where is the SDSL paper? And also, do you believe that Puzo's incorrectness logic lets you treat debuggers as theorem provers, quote unquote, can be integrated with LLMs, considering more people are using debuggers in conjunction with LLMs from their terminals?
Okay, so first question, the SDSL paper was in FMCAD, I think 2023 or 2024. Anyway, you'll find it there. And sorry, I didn't catch the second question.
Yeah. Do you believe that Kuzo's incorrectness logic lets you treat debuggers as theorem provers, quote unquote, can be integrated with LLMs, considering more people are using debuggers in conjunction with LLMs from their terminals?
Okay, there's a lot of stuff going on in that question. I'm not super familiar with the Cuso's thing, but I mean, I do think that LLMs are very useful as debuggers, right? And there's a lot that can be done to push, you know, there's a lot that can be done to push traditional testing and software engineering using LLMs. But at the end of the day, I'm a formal guy. I don't think you'll get all the way there. There's only one way to get all the way there, and that's formal methods. So I'm gonna, I'm gonna chase down that approach. But certainly, certainly, I believe that LLMs can improve many, many other aspects of coding. Okay, so let's talk a little bit about this, right? So what does this backend look like, and what does Bool look like? So the idea is Bool should be a language that looks like pseudocode. It should be easy for humans to understand. It should be embedded in Lean, and we should absolutely try to minimize the trusted computing base of anything we're doing when reasoning about Bool. And the verification conditions generated should be Lean goals and should also be readable. And these principles are based on, bad experiences with existing tools that don't have these properties, and it becomes almost impossible to debug or modify them. So let me show you another demo. Okay, so let's see. Uh-oh. Oh, here we go. Okay, so here we have a little program called find max. The purpose of this program is to find the maximum value in a vector. And as you can see, we've written it in this language called Boogie. Boogie is essentially the starting point for Bool. So if you're familiar with Boogie, this is an intermediate verification language developed many years ago by Rustin Leno and used as the back end of a bunch of verification tools, including Daphne, Viper, MoveProver, a bunch of other stuff. So it's quite successful as a language, and I like it as a language. I'm not I should be careful here. So the tools that were built around Boogie, I think, are a bit old and need to be updated. But and I wanted to update them using Lean. But the language itself is nice. So you can, write a little piece of code like this. Um, and notice though that this is all written inside of Lean. So this is written using the Strata package that I mentioned. Strata gives you a way to just say, pound Strata, and then you can write your Boogie code. And all of this gets, compiled down into data structures inside Strata, inside Lean. So now what we can do is we can say, my students have written this little function called generate SMT VCs, and this will traverse the Boogie code and generate a bunch of verification conditions in an SMT-like language, but in Lean. Now, it looks like this, which doesn't look very helpful, but if you just focus on, let's pick one of these verification conditions, say like this entry invariant. Okay, so if we go to that one, it looks like this. And then if we just do a couple of intro rules, now it looks much better, and we can do a little bit more massaging, and it looks like this. Okay, so this goal, if you stare at it a bit, you can see that this is trying to prove that if you enter the function and assume the precondition, then the loop invariant holds on the first iteration. So how do we know that? Well, look at the hypotheses. We have n greater than 0, that's the precondition. And the other hypothesis is 1 less than n, which is actually the loop condition once you substitute 1 for I. And the gen SMT VCs does a little bit of constant propagation, so that's why you get this 1 less than n. And then if you look at the thing you're trying to prove, we have n greater than 0, and this thing is true because I is 1. This 0 less than or equal to I, and then I less than or equal to n right here is 1 less than or equal to n, and so on. So you get the for all and the exists. So basically, this is something that I can look at my original program, and I can look at my goal in Lean, and I can understand it, right? And say, oh, okay, I'm trying to prove this particular path through the program respects the conditions. Okay, and now we can actually prove this goal and all of the goals just with the SMT tactic. So I think this is pretty exciting. Like this is sort of, the first thing we're doing. We've started extending Boogie. We've added arrays and for loops, right? So something that wasn't in original Boogie is now in Bool. So that's kind of the direction we're going. We're working through, an algorithms textbook, trying to write all the code there in a nice, clean way, extending Bool as we go. Okay, so I have one more little section here, which is what about this part? So remember I told you with the Clover work, we sort of did a proof of concept that maybe you could generate formal specifications. So since then, we've done quite a bit more. So I'll tell you about that last. So this is about AI-assisted specification generation. It's another project with a bunch of collaborators being led by my student Livia. So here the idea is, suppose that we start with some code and some tests. Maybe this is legacy code, maybe this is some standard library code, and we want to now add specs to this and prove that it's correct. Okay, how are we going to do that? All right, so what we do is we have basically an agentic framework. We have a bunch of modules that know how to write specifications. They can also write these module level things called views and type invariants, and then they can do proofs, which help with they're basically little lemmas that are needed to help the verifier go through. We have a planner module that decides which of these things you need. And then we have these repair modules where if if the verification doesn't go through, we try to see why. We have different approaches that can be used to repair it. And then ultimately at the end, we are hoping to produce this verified code. Okay, so for this demo, I'm going to show you, okay, so this is Rust code, and we're verifying it using the Varus system. Now, Varus is not using CSLib yet. So new project, we're just starting the last couple of weeks, is we would like to hook up Varus to have a CSLib backend. But right now, Varus does its own translation to SMT solvers. It's all untrusted. It's not embedded in Lean. It's doing the sort of old school standard verification approach. So we're using that tool for this demo. Okay, so what we have over here is we have our AI agent. And on the left here, you can see the code. So initially, the code has no specifications. And the sort of first iteration just says verification failed. And that's because there's no specifications. So it says, all right, we're going to add some specification clauses. So if you look over here now, we've got a requires and ensures. And this is done fully automatically just by prompting a language model to analyze the code and come up with the pre and post conditions. But this is not good enough. We also need a loop invariant. So then we do some refining of the proof. And now if you look over here, we've got the pre and post condition. We also have the invariant. And now it says successfully verified. Okay, so this is a paper we just submitted, and basically it shows that we can do this kind of auto generation of specifications for something a little more complicated than this. Basically, sort of a data structure module in Rust. We looked at, for example, a ring buffer. So you've got, some way of pushing and popping things off the buffer. And we show that all of these methods together are correct. We generate the specifications and prove it correct. And we have about 10 different benchmarks like that. Here's the analysis of that from that paper that shows that we just run an LLM and say over and over again, please verify this program. We're able to verify, about 52 out of 129 verification conditions in this suite of benchmarks. But our tool is able to do almost everything, all but one. And basically, it does this by iterating, by repairing, by using these different modules to try to add the specifications. All
There
right,
is a
so I think this
question.
is pretty exciting too. Yeah.
Yeah, it is. There is a question in the chat. How do you know the auto-generated specifications are what you intend?
Yeah, good question. So we haven't done this yet, but the idea would be to integrate it with something like the Clover approach, where you would check the consistency of the natural language and the code and the specifications. And then, as long as the human has read the natural language, hopefully then you can be confident that it's correct. I have another answer for that though, which is I think especially if you're writing new code, or if you're having AI generate code for you, this first step of how do you capture the human's intent, I think is a really interesting problem. And I would love to see more research on that, where you have some AI agent that is, having a conversation with the user, showing different scenarios, getting feedback, using all of this together to compile a rich specification. I think that's a really interesting research direction too.
Uh,
Yeah,
Another
another
question
question.
from David.
uh, as as is the academic mode, more of a comment than a question. But just you keep on mentioning human in the loop for reading the description, and I just feel like it's important to point out most of the time human in the loop means that you tell somebody to do something and then they kind of glance at it and they don't do a good job, and that seems like the almost certain kind of second step of like, oh, you're just going to tell it, somebody to look at it and they're going to do better. So it would be good if we had something slightly more robust
Yeah.
than tell somebody they're really supposed to look at it. That's all.
Yeah, I agree. In fact, so I would much prefer that rather than, having somebody whose job is to read everything after the fact, right? I would prefer have the human involved at the beginning and say, okay, you want some code. What do you want? And have this conversation with the human before they get anything, right? And then really force them to go through a very rich requirements engineering process, which I think can be assisted by AI in a lot of interesting ways. So that would be my preferred method. Yeah, I don't I agree that the sort of human in the loop when everything is almost always correct means that the human will never find the problem. All right. Okay, so we're about done. So the just kind of talking about what we're doing for next steps. We'd like to move to larger, more complex programs in Boole, and we'd like to look at ways of interfacing with realistic programming language. Like I said, we're going to start with Rust with the Varus project. I believe the Strata team at Amazon is starting to look at Python front end for Strata. So, this is starting to happen, and that's exciting. Of course, we do need better automation for theorem proving in Lean. And, we have there are lots of efforts there, like I mentioned, including our own Lean SMT effort, and including all the startups who are trying to build, AI assisted theorem provers. So I think that's going to move ahead quickly. And then ultimately, we want to build up a library of verified programs. And here we're hoping to collaborate with the Verilib folks. I know some of you are on the call. I think it'd be great to have, you know, some kind of agreement there where, when we generate some verified Boole programs that we're happy with, they get put into Verilib, and this would be a nice way to synchronize with some other efforts. All right, so that concludes, and I'm happy to take any additional questions.
Thank you so much for the presentation. I think time-wise, we have, yeah, something like 5 minutes. And there is a question in the chat, but the recording, so where will the recording be posted? You will receive an email about it, and it will be on YouTube. We have a question from David.
Yeah, so I'm just wondering, a bunch of this overlaps with the safeguarded AI program in the UK. I don't know. I'm just wondering how much you've been in touch with them.
So I know those people. I don't know that. I mean, hopefully, they will, jump on board the CSLib bandwagon and we can coordinate. I hope they're not doing something in that direction that's totally different. But yeah, I mean, when I talk to AI safety folks, they are thinking 20 steps ahead and I'm thinking 2 steps ahead, right? So it's like, they're like, okay, so once we verified all the software, here's all the things we have to do. And I'm like, great, you guys think about that. I'm going to try to verify all the software.
Yeah, I think they do have some applied work, but the computer scientists that were kind of part of the first program group, when they discussed this, nobody was really interested in actually doing the hard work of putting things together in Lean, unfortunately. So it's really great to see that you're doing it. I just wanted to know that like there had been communication.
Yeah, yeah.
Uh, any further questions from the audience? Um,
I have a question. It's kind of not directly super related to the presented technical content, but more like the practical next steps. So if people would want to engage with this, apply it, or try it out, or learn more about it. Okay, you have already shared some kind of resources, of course. But for example, I was interested in this Boole language, right? So if
Yeah.
I wanted to learn more or engage with that, what would I do?
Yeah, so the easiest thing for now is there's a CSLib channel on the Lean Zulip that you can post questions to. We are currently writing a white paper about CSLib, which we will release and announce there, that spells some of this out in more detail. And then I think once we release the white paper, we'll also send out a call for engagement, and we'll have, a bunch of things that people could get involved in. We're still kind of, it's a little early to do that because we're just, building a bunch of nuts and bolts infrastructure to make anything work at all. But we're getting close, and we do a lot of this is available already in open source repositories. So feel free to go to the Lean CS lib zulip and ask any questions. I'll be happy to point you to the Strata um, repository, the CS lib repository. You can see what's taking shape there.
Thanks, yeah, the strata I already found.
Great.
so I think for today, we're pretty much about time now. So thank you so much, Clark, for this presentation and for everyone to have participated today. We'll see you at the next one next month. And I'm sure if there are further questions, we can email you. And
Yeah,
so
it's fine.
thanks so much and see you.
All right. Bye-bye.